Hey guys, Mr. Brown here, and this set of slides is for Chapter 3 from Klein's 4th edition of Organic Chemistry. And Chapter 3 is all about acid and base interactions. We're going to learn how to identify them, draw their mechanism, and predict the position of equilibrium for some acid and base interactions. So on this slide, we have a review of Bronsted-Lowry acid-base theory that we learned in general chemistry. And what we learned was Bronsted-Lowry defined acids as anything that can donate a proton. So it will give a hydrogen nucleus, not the electrons, just the hydrogen nucleus, from one molecule to another. And whatever molecule is giving away that hydrogen nucleus is the acid, and whatever molecule is receiving or accepting the proton is called the base. We see an example here of hydrogen chloride reacting with water to form what is commonly called hydrochloric acid. And we know that the hydrogen chloride is the acid because it gives away a proton to the base, which in this case is water. And this is what happens when you mix hydrogen chloride with water. A chloride ion is formed by way of giving the proton to the water molecule, forming H3O+. And remembering some terminology, the acid forms the conjugate base, and the base becomes a conjugate acid, because we want to keep in mind these are equilibrium processes. So while this takes place, we would see a very minute amount of the conjugate acid coming back the other way and becoming HCl and H2O in the other sense as well. So in that direction, the H3O plus is giving a proton back to the chloride ion, reforming the HCl and the H2O, and that's why it can be called a conjugate acid and a conjugate base. Here on this slide, we have another acid-base interaction, and this time we've included curved arrow notation. So as you can probably imagine, acid and base interactions are really common in organic chemistry. Our molecules that we've studied so far and will continue to study have lots and lots of hydrogens floating around in them at different points, and those hydrogens can get traded back and forth quite commonly. And we use this as a good introduction to the type of notation that's used to show all reaction mechanisms throughout the organic chemistry literature, and that is the curved arrow notation that you're looking at on this slide. This shows what we call the reaction mechanism, what is actually taking place in this particular acid-base interaction and in all reactions that we study. It shows the flow of electron density in a reaction, and it's important that the tail of our arrows always starts on a pair of electrons, whether that is a lone pair of electrons or a bond. The tail of the arrow should always start on some electrons and then go to an atom to show a bond form. So it shows an electron either that's already in a bond or a lone pair of electrons going to another atom and forming a bond with that atom. And the curved arrow should always behave that way throughout all of the mechanisms you draw for organic chemistry. In acid-base reactions, the base's electrons attract and deprotonate the acidic H or H+. It takes away the proton. So the base's his electrons, usually a lone pair of electrons, takes a hydrogen away from another molecule, and we see that demonstrated in the reaction here at the top, where the base is a hydroxide ion and the acid is some organic carboxylic acid, and it's easy for that base to come in there and to deprotonate that species. And we see the reaction arrow there where we show the lone pair on the hydroxide ion forming a bond with the proton on the other molecule. And then notice that the electrons here in this bond stay with that oxygen and form a lone pair on that oxygen. So and that's how the acid-base interaction should be shown in all of our future drawings of acid-base mechanisms. The electrons in the bond holding that hydrogen on the acid stay with that species afterwards. We have our first set of questions on the slide. We're going to try to determine the mechanism of these acid and base interactions, as well as try to identify the acid, the base, the conjugate acid, and the conjugate base. So looking at the top one here, when I'm trying to determine what happened during this acid and base interaction, I'm going to look at what takes place in the reaction overall first. And so what I see here is an OH. The first thing that kind of jumps out to me is the OH becomes an HOH in this molecule, or in this reaction, if you will. The OH here clearly becomes an HOH, and the hydrogen disappears here, so that's probably where it comes from. And so if I'm trying to draw the mechanism for this reaction, I'm going to show the lone pairs here on my hydroxide ion, and I will show one of those lone pairs forming a bond with the hydrogen there. Remember, the electrons in the bond with the acid stay with the acid, and so I would draw another arrow from the bond to the oxygen atom holding that proton. Since the species here on the left gives the proton away, this is the acid. The hydroxide ion removing the proton would be the base. And then on the product side, the newly formed water molecule would be the conjugate acid, while the newly formed oxyanion here would be the conjugate base. Showing the next one here, I see that an H3O plus ion here seems to give away one of its protons to the ketone species that we see. And a new hydrogen kind of appears in this species, whereas one disappears from here. So I know that hydrogen moved from that molecule over there. So if I draw in the lone pairs, I would show one of these lone pairs forming a bond with the hydrogen, and then the hydrogen leaving the electrons in that bond with the oxygen. This species accepts the proton, so it is the base. The hydronium ion gives away the proton, so it is the acid. That makes this species the conjugate acid because the base becomes the conjugate acid. And that makes this species the conjugate base because the acid becomes the conjugate base. In the next example, I see a hydrogen that seems to appear from almost nowhere, become bonded to a nitrogen, and a carbanion appear on the end of my carbon chain there. So one of the hydrogens came from the methyl group there beyond the carbonyl oxygen and was bonded with the hydrogen. So there's a carbon here with 3 hydrogens, what used to be 3 hydrogens. And over here, one of them has disappeared and a new hydrogen has, or that hydrogen has bonded here to the nitrogen. So if I'm showing that, I might be able to show my lone pairs and one of them bonding with one of the hydrogens, which does leave those electrons there with the carbon, forming the carbon ion that we see there, making this the acid because it gives away a proton. This is the base because it receives the proton. This then therefore is the conjugate base, and this is your conjugate acid. I think that's enough demonstration for those, and I'll leave the last couple to answer for you.